So recently, I've been learning OpenGL. OpenGL is a graphics API that allows us to draw stuff on the screen and eventually create experiences such as games or game engines. Usually, most games are not made using OpenGL, but rather a game engine or a game library. Since using a graphics API is much harder, since most of the things you do, you have to do yourself, and you have to build most of the stuff yourself. There are multiple graphics libraries I could learn, but I ended up deciding in OpenGL because Vulkan is hard for beginners and I wanted something that's cross platform. To be specific, OpenGL is not a graphics library, but it is a specification that allows us to interact with the graphics processing unit, which is the GPU, which allows us to create graphics. OpenGL initially started with limited features and much easier than it is now, with more straightforward stuff for creating graphics, but making it less flexible. This is called Legacy OpenGL and it is much easier than modern OpenGL. Of course, I'm gonna focus on modern OpenGL, and how am I gonna learn it? By making a 3D renderer. The resource I mainly use for this is learnopengl.com. I'm learning OpenGL using C++ since honestly I'm much familiar with it than the other options. And before we get started, this API is inconsistent garbage and makes me want. Anyways, so the first step was to make a window, of course. Doing this can be done by using this library called glfw, which allows us to create a window, process input, etc. First, we just call glfw init and initialize glfw, and then we give it hints about what OpenGL version we want to use. We then create a window of the type glfw window pointer and give the window its height width. Then we just need to tell glfw to make the window the current context. So yeah, that's basically it. Now if we run it, the window closes immediately as the window memory is freed after it goes out of scope. So we just implement a game loop that runs when the window should not close. And here we just change the color and poll the events and swap the buffers, for which OpenGL uses a double buffer system. Now we have a nice window. Now let's get started with OpenGL and create the first triangle. But first we need a function loader to load the functions at runtime. For this we can use glad, glue, and many more, but I decided to go with glue. For this we just need to include glue and make sure it's included before glfw, and then call glue init when there's a valid glfw context. Okay, so now how can we draw a triangle? For this, first we create this thing called a vertex buffer object, which just holds a block of memory and in this case holds information about the vertices. For now we just care about positions, so let's put the position of each vertex of the triangle. After that we can just call these functions and bind it to the GL array buffer target. Now is a good time to mention that OpenGL functions as a state machine, so it can only have one state at a time. So for this we can bind and unbind buffers of memory, as you can see. Now next we have a vertex attribute pointer to tell OpenGL how our memory is actually laid out. For this we need several stuff. The first thing we need is the index of the attribute. This will come in use later. The second is how many elements we have. The third argument is the data type of the data type we are passing in, and the fourth argument is if we want the data type to be normalized, so in a range of 0 to 1. The fifth argument is the stride, which is the byte offset between elements in your VBO. So how many bytes OpenGL has to move from one attribute to go to the next attribute. Right now we only have positions, so it's just the size of 3 floats. The sixth argument is the pointer, and it's a void pointer or offset to the location where the vertex attribute starts. For us, the position starts immediately, so it will just be 0 for us. Now next we need a VAO. A VAO is a vertex array object that connects the vertex array object and the vertex attribute together. So whenever we want to use it, we would normally need to bind the VBO and the vertex attribute over and over again. But with VAO, this process is simplified. It's simple enough to make with just these functions. And when we need to use it, we can just bind it. As previously mentioned, OpenGL functions as a state machine. Waiting for the triangle. We are still not done. We need shaders now. It's normal to associate shaders with stuff such as lighting, shadows, but that is just not what shaders are. In the most basic forms, shaders are programs that run on our GPU. There are many types of shaders, but the main ones are fragment shader and vertex shader. The vertex shader is run for every vertex which is drawn, and the fragment shader is run for every fragment that is drawn. A fragment is a pixel, not really, but for now, just assume it is. We first create a vertex shader, and for shaders, OpenGL uses a language called GLSL, which stands for OpenGL Shader Language, and it is C-like. First, we define the version we are using to GLSL, and we have this main function. First, we take in a variable at location 0 as a position. This location is the same as the index in the vertex attribute pointer. And in the main function, we just set GL position, the position of the current vertex, to the position from the vertex attribute. Now for the fragment shader, we pass a vec4 variable called frag color out, which is just the color of the current pixel. And in the main function, we can set the color of the current pixel to anything we want. And now finally, we can go into the loop and we can draw by calling this function and specifying the primitive we want to draw. If we want to draw objects such as squares, we can see that we reuse our vertex. This causes redundant data. To avoid this, we can use index buffers, which uses index to draw vertices like this. It's similar to creating a vertex array object, and we specify the indices. So for a square, it would be like this. And yeah, we also changed the code for drawing to this. And yeah, all that for a triangle. But now let's make the triangle cool. We actually can pass variables between shaders. So if I go into my VBO and add a color for each vertex and adjust my vertex attribute pointer accordingly, and in my vertex shader take it in and pass it into the fragment shader and set the frag color to that variable. If we do this, we get a cool little effect like this. Cool. Well, now it was time for abstraction. It's important to abstract stuff in OpenGL, otherwise you'll be writing a lot of code. And plus, I was also needing a shader parser to parse a shader file into a string, so I could also do that. The shader abstraction has the following functions. Set shader is for setting the file path of the shaders, and compile shader just turns the file path into a shader and compiles them together in a shader program. A shader program is needed to link shaders together. Think of it like similar to the C++ linker. After that, we can just delete the shader since we don't need it after we link it to the program, since we can just bind and unbind the program when necessary, which is exactly what the bind and unbind functions do. We also need these two functions which checks the errors caused by the shaders and the programs. Next, I just made the same shader abstractions for the vertex buffer object, as you can see, the vertex array object, and finally the index or element buffer object. Now the code looks much cleaner. Next, let's implement textures. A texture is a 2D image, also even 3D, that holds an array of pixel data. Textures allow us to render any image we want in our renderer. Let's get started by talking about texture wrapping. When we assign a texture using texture coordinates, it's usually in a normalized range from 0, 0 to 1, 1. But what happens if we specify coordinates outside this range? Well, we can choose what will happen. The first option is to repeat the image, which is self-explanatory and looks like this. The second option is mirrored repeat, which is the same as repeat, but it mirrors the image. The third option is clamp to S, which causes a stretch-like effect. And the fourth option is to specify a border color, and that coordinates outside the 0, 0 to 1, 1 range will be a specified border color. Next thing to decide is texture filtering. You may recognize this term from game engines where you usually use nearest for pixel art. Texture filtering is important so that OpenGL can recognize what value to assign to the texture pixel. Well, there are two main types of texture filtering, which is linear and nearest. Linear uses linear interpolation and smooths the transition for pixels, while nearest uses the nearest pixel. Next, we have these things called mip maps, which are just textures but lower in resolution to be used when the texture is viewed from further away. We can use two main types of mip maps, which are linear and nearest, similar to filtering. Linear interpolates between the generated mip maps, while nearest uses the nearest mip map. Now, finally, we need to load the image. For this, we can use a library called htb image. We just bring this header into our project and create a C++ file where we include the header and define htb image implementation and compile the cpp file, and finally include the header in our C++ file. First, we define these variables, which will store the height, width, and the channels of the image, and then call stbiload function with these arguments. Then we can create a texture and bind it to the GL texture 2D target. Next, we can generate the image from the data using GL text image 2D, which takes these arguments. And finally, generate mip maps with the target as the singular argument. Next, to see the texture, we need to put the texture coordinates in our vertex buffer object. Remember that it's in a range of 0, 0 to 1, 1. And then we need to adjust the vertex attribute pointer and create one more for the texture. Then in the vertex header, we can take in the index and access the texture coordinate and pass it into the fragments header, where we use a uniform in this way and use this texture function. Next, we just need to assign it to the texture unit we want to use, and yeah, we have an image. Okay. Next, I just abstracted the texture into the texture class. Of course, boring stuff still necessary. Okay, so till now everything is pretty 2D, but now we get into the fun part, making it 3D. For this, we need three main matrices, which allows us to transform space using linear transforms. These are the projection matrix, the modal matrix, and the view matrix. The projection matrix mostly handles projection, which takes in the FOV, the length and the width of the viewport, and also the near plane and the far plane. The modal matrix handles scales, transformations, and rotations, and changes the modal coordinates into world coordinates. The scale and transform matrices aren't that interesting, but just look at the rotation matrix. It's just beautiful. And finally, the view matrix, which transforms world coordinates to what the camera should see. We will talk about this further later. And now, if we just use the modal matrix to rotate our square, we get this. Cool. Now it's time to create our camera. So it's just the view matrix for which we use the look at matrix. I'm not going to get in detail, but that's basically it. Now let's make some flying movement similar to 3D modeling softwares or game engines. For this, we can use the process input function, where we set the camera speed and multiply it with delta time, which is basically the time since the last frame, calculated as this. So whenever the player moves using WASD, we can just change the camera position accordingly. It is pretty straightforward for forward and backward, but for left and right, we use the sneaky little trick by getting the cross product of camera front and camera up to get camera right, and voila, we have movement. But still, we can't move the mouse around, and honestly, I forgot how most of this actually works. I'm just gonna tell you what I remember. We first take a callback for whenever the mouse is moved, which gives us the X position and the Y position. Okay, so first there are two important things to talk about: yaw and pitch, with pitch being the up-down motion and yaw being the left-right swing motion. After we have this, we can just use some trigonometry to get the rotation and apply it to our camera with the following code. We also define a sensitivity to severely reduce the rotation, and that's basically it. Next, I just started zooming by scrolling, which was much easier. After that, I created a camera class like this, and also put the projection matrix and the view matrix obviously into the camera class. So that's it for this video. I'll upload more parts into the future, but this is it for now. Thank you for watching.